equals VWX, and there's conditions on this, and VW is less than N, W greater than 1, same conditions as before. For every single way to split it up, there exists some I. You're going to have to exhibit some number bigger than or equal to 0, such that VWIX is, and finally, not in L. It's my job to come up with a number so that when I pump up the string at the loop that they told me where it was, I get a new string which is not in the language, guaranteed, and it's supposed to be, so therefore they're lying to me. That means their machine doesn't satisfy the pumping property. That means their machine doesn't exist. That means there is no finite state machine and the set's not regular. This is what we're going to be using in the examples. And we're going to do 2 or 3 examples now and make sure everybody gets the idea, following this very formal structure in a more intuitive, logical way on the other side of the board. OK, questions about this? Who's getting this? Nobody? All right. Yeah, Todd.
We said V didn't have any loops. We formally said that. Doesn't matter.
We said we have
no loops in V. The W is the first occurrence of a loop. Where do we write that?
That's actually, it's not actually implied by the way I wrote it down. It is conceivable here that there are loops in V. It's this condition. I didn't prove this lemma, right? I just told you it was true. Yeah. But the reason this lemma is true is because the hard part is that VW has to be less than or equal to N. I know VW has to be less than or equal to N because I know there's going to be a loop that shows up there. And I'm saying that we'll call the first such loop W. So we're going to end on that. But it's possible that the person might actually be able to satisfy these conditions and have W be the second or third loop. That's true. So there's no guarantee based on what I wrote that there can't be any loops in V. But the fact that this is less than or equal to the N is implied by the fact that I know there has to be a loop, at least one, in N. But yeah, maybe you could have loops in V. That's possible. Yeah.
So in other words, if you can break it, it's a regular set?
If you can break the pumping property?
Yeah.
Yes. Okay. No. If you show that this pumping property is not true, then it's not a regular set. If it is a regular set, then you can pump the thing up over and over and over and over again. Right. But the converse of this, Joe, this isn't true. I can't just reverse this arrow. If you have a set and you show that it has the pumping property, you know that you can always pump things out of it, it doesn't mean it's necessarily regular. There are sets that are not regular that still happen to have the pumping property. So you can't always use the pumping lemma to prove that every single set that isn't regular actually isn't regular. I might give you a set that isn't regular that actually satisfies the pumping property, and you'll never be able to show the pumping property doesn't work because it really does work. So this is not an if and only if. It's not enough just to examine the pumping property of a set to decide whether it's regular. Most examples you'll see don't satisfy the pumping property, and it is enough, but some will occasionally. Yeah, I'll do an example where it does later on today. Yeah.
What part of this indicates that W is the first loop? I mean, in the writing of it.
I think that's what Todd was kind of getting at. The part that really indicates that is it's less than or equal to N. I'm guaranteeing the W is a loop, and I'm forcing my opponent to find that loop in the first N symbols. It doesn't have to be the first one.
It seems to me that
tell me any loop that occurs in the first N.
W to contain a loop, but that, for example, the loop might start 4 letters into W. That you're not.
No, well, I'm asking them to call W the symbols that are on a loop.
Well, you ask your opponent.
Right.
You
right.
ask them, but in this, the actual definition, I don't see anything that forces that.
There is nothing that forces it.
So it sounds like you're putting an extra restriction, giving your opponent an extra restriction more than what the property actually indicates.
Well, you know what? I won't ask my opponent anymore for the very first one. I'll just ask them for any loop that occurs in the first N symbols. That's enough too.
Actually, I'm not concerned that it is the first loop. I'm concerned that you're asking them specifically for a loop. Because this W could contain a loop, but it doesn't. The way I'm reading this, W isn't only a loop. It must
No,
be
W is only a loop.
and something else.
No, it's not.
Why is that? What part of what you've written here specifies that?
This part over here, the part that I can pump it up, or the part that I can pump it up and it's still in the language. This says that there's some way to split this up into 3 parts so that I can pump up the middle part.
Okay.
That some way is going to be by finding that loop. And I can force my opponent, when they find it, to find it somewhere in the first n symbols. But you're not concerned about that. You're saying, where do I know that it's a loop? I know that it's a loop because of this consequence.
Right. Okay.
Okay? All right, other questions? I think we're ready to do some example. Okay, let's do the example that Dimitri wrote on the board yesterday, palindromes. 1L in palindromes?
Yeah. From the Greek, running backwards.
Yeah. All right. We want to show that the set of palindromes, those are things that read the same way right to left as they do left to right, that those strings, say over the binary alphabet 0, 1, that they don't satisfy this pumping property. Let's follow through our dialogue the way we did it yesterday and notice how it really goes along this set of criterion. I'm going to imagine that one of you went home and came up with a finite state machine that does accept palindromes, and I'm going to ask you how many states were in that machine. Or, according to this picture, for any n in the whole world that that person tells you, you've got to be ready for the next stage. Okay, so here's how I would write it. My opponent's machine has, let's call it k states. Okay? That's the for all. I got to be able to handle any number. Here I called it n, here I call it k. My opponent's machine has k states. You want to do it with an actual number like 50, or is k okay? K is all right? All right, my opponent's machine has k states. Now it's my turn. I have to show that there is some string in L that's longer than that number of symbols, k, such that all this stuff is going to work out. Now, what I want to do now is pick a bad string. Because when you first do these pumping lemmas, it's hard to look in advance to see what string you're going to need, because you're just getting used to it and you're a beginner. And you kind of hope you get lucky. So I want to get unlucky once, and then we'll get lucky the second time. All right, let's get unlucky. Let's come up with a palindrome that has at least k states. Here's a palindrome that has at least k states. 0 to the k, I don't know, k divided by 2, 1, 0 to the k divided by 2. Right, that's got at least k states. I put half k zeros on one side, half k zeros on the other side. I put a 1 in the middle. It's definitely a palindrome, right? Whatever the half of the k is, it got it on both sides. I got a 1 in the middle. It reads the same right to left. So I pick z equal to this. And I know it. I should make a little comment on the side. Note, z is in L. That is, it's a palindrome. It's a palindrome. Latin for running backwards.
Maybe the borrowed
Z is in L. It's a palindrome. And what else? And z has more or equal than k symbols. Okay. So I'm okay so far. I got through the second stage. Now it's my opponent's turn. Now I got to handle any possible set of 3 things that equal this string. So my opponent sets